I won't just totally confuse everybody today because I'm still not at 100%. So we're gonna kind of work it. We're gonna work a bunch of problems. I do have the record button and it looks like it's recording. We'll see how it goes. Let's look and calculate the magnetic field due to a high voltage power line. So we're going to say that it's 20 meters off the ground for high voltage power lines. And if you look at a high voltage power line, if I'm looking at a typical power line, they're saying that they're running at 765 kilovolts on a 100 or 1000 megawatt system. And I actually got that data from the Wyoming Power Company for their high voltage lines that are going through Wyoming. So I feel pretty good about those numbers. But if we want to do that, one of the things that we know, if I've got voltage and wattage, I've got to have current, because the magnetic field, the magnitude of the magnetic field is going to be based on what we based on what we showed and worked on Wednesday. So that's going to give me the field. So I've got to figure out current. And to figure out current, we can go back to my power equation. So power is going to equal either I squared R or it'll equal VI. So we're going to use the VI part. And so 1000 times 10 to the 6 watts divided by 765 times 10 to the third volts is going to give me about 1300 amps. Or we're going to do about 13. So for this calculation, we're going to look at about 1300 amps. And I don't know, I guess it was the first I'd heard of it, by the way, a couple of days ago when I was watching a little bit of the baseball game. They're doing, what they call it, current wars, I think is what it is. It's the fight between Tesla, Westinghouse, and Edison about which electrical system is going to win out. And it's an interesting fight because there's also, what they don't tell you is J. Paul Getty gets involved. And it's the money, it's the same money barons, you know, the Rockefellers, the Gettys, all of those that also influence who are the money backers between the different ones. And of course, Tesla is the one that died destitute in a hotel room in New York City. There's lots of conspiracy theories about that one too. That supposedly the FBI came in and raided the hotel room and took everything. It's kind of weird, you know. Totally weird conspiracy theories, but they're out there. But I'll tell you, the fight got bad enough that I think it was Edison who electrocuted the elephant to show that one method was more dangerous than the other. So it's kind of an interesting, it's an interesting case in history that's out there. So it's pretty gruesome. So if we do that, that gives us our current. We've got the radius and our current, so we can calculate the magnetic field. So if I plug in my numbers, I end up with, this becomes 4 pi times 10 to the minus 7 divided by 2 pi. That's my mu over 2 pi. My current is 1300 amps divided by 20 meters. That ends up giving me 0.0004013 Tesla, or if I write it out there, it's 1.3 times 10 to the minus 5 Tesla. And if you want to know a safe magnetic field, to get an MRI, to get a good high density MRI, you're between 0.5 and 1.5 Tesla. So even a high voltage power line isn't going to even tweak a compass, you know, if you're sitting under a high voltage power line. So all of the hubbub about living under high voltage power lines is pretty much, nah. It's not really, there really isn't truly a big effect about living under a high voltage power line. And to be fair, the data was reviewed and revoked, and the people who actually did it pulled it out. It was still a good study though. They just had an uncontrolled variable, that's all. All right, let's look at a wire. So we've got a wire. We've got current going in the wire that way. We've got current going in the wire this way. We're going to look at a point A out here. We've got a point B halfway between and a point C out here. This is, I think we've got the distance between them are D, and this is 2D. And we want to find the magnitude of the magnetic field at these 3 points. So when we do it, we're going to say out is positive and in is negative. So if I am doing, this is wire 1, or this is wire 2, and this is wire 1. Okay? So if I'm doing it, I've got B is going to be mu 2 pi I over R. But we're going to do net, so we're going to add or subtract depending on what we get. So B net is going to be the magnetic field due to wire 1 plus the magnetic field due to wire 2. So if I'm at A, B net is going to equal mu divided by 2 pi, whatever the current is, and if I'm doing it from, so if I'm doing it from 2, put my thumb on there, curl around, and I'm coming out of the paper there, so that's positive. That's 1 over 2D for coming out of the paper because my thumb goes in line with the current. Curl it around, the magnetic field's going to come out of the paper, so that one's positive. If I'm doing it here, my fingers are going into the paper, so it's negative, and that's 3D away. So that's going to be my net magnetic field for the 2 wires that are going right there. So now if I do it at B, the magnetic field net. So in this case, if I'm doing it at B, my thumb goes in, my fingers are going into the page. So that's minus, because I'm at D over 2. And I'm going here, my thumb is in here, going this way, it's going, if I get my fingers all around, it's going into the, it's coming, got my fingers twisted backwards here, but it ends up being minus D over 2. So that's that one. Fingers going in, it's negative. If I come over here, now that actually goes that way. It's positive, it cancels each other out. Oh, it should be additive, hang on. So going in, yep, that's going in. This one, if I turn my fingers slow in, it's going in. Yep, that's the way it should look. And then at C, so at C, I'm at minus 1 over 2D. And at C, I'm coming out of the paper, so that becomes plus 1 over D. Oh, that is a minus. because this would have been additive, because I'm going into the paper that's negative, so that's a negative negative. This one is a negative plus. You guys are not hollering at me about getting it up there on the paper. So you can do those kinds of problems. Then we do terrible things like this. All right, so I've got a wire that's connected to a resistor. I have magnetic field is coming out of the, or going into the page. We have a bar, that's a conductive bar, that we're moving at 0.25 meters per second. The spacing between this is 0.25 meters, and the magnetic field has a strength of 2.5 Tesla. We want to have a specific current in the bar. The current we want to have is 0.5 amps. So we want to know what the resistor has to be. Okay? So we know that our EMF is equal to IR because we've been beating that into our heads for the last 3 weeks. We know that the force, the magnitude of the force, because we're perpendicular, is going to be QVB. And now we've got our electric force, which is QE. We haven't shown this yet, but this is the perfect one to show it with. There's a relationship between the magnetic field and the electric field, which we've already kind of know because we've been talking about it, that my magnetic field will induce a current, my current will induce a magnetic field, but now we get to see it straight up that we do have a difference. Okay? So the electric field and the magnetic field are related. There is this difference that I have that changing magnetic field part, that I've got motion. And we've also had that my change in potential along the way was equal to E times L. Okay? So now we can put in my E times L, so I'm going to put in for B, or for E, I'm going to put in my V for that. So we get that. And if we go back and look at Faraday's law, this was my change in my Gaussian with respect to time, which becomes my flux associated with my magnetic field with respect to time, which area is, in this case, L squared with respect to time. But I can separate my L, right? I can make that BL times L divided by T, but we know what that is. That's the velocity, so now I can get BLV. And we know that IR is equal to my EMF, which is now BLV. I equals E over R, which now is BLV over R. And we're trying to solve for the resistor. Trying to solve for the resistor. So I get R is equal to VLV divided by I. Now I can plug in numbers. 2.5 Tesla, 0.25 meters, 0.25 meters per second, divided by my 0.5 amps is going to give me 0.3125 ohms. And here comes the fun part. If we want to prove the units work out. Okay, that's Tesla meters per second divided by current. Well, current, if I get that right, I end up with volts, seconds, meters squared per that, which those cancel out. Somewhere I've lost something. Because I ultimately should be in volt amps, and volt amps give me resistance. I lose that second somewhere along the way. Oh, because I didn't have it there. There it is. Aha. That's where it goes away. I didn't have it right there. So just kind of giving us back, if I have just a charge, the force is Q, V, B, sine of the angle. If I have a wire, it's B, I, L, sine of the angle. So that's for a charge, that's for a wire. So if you're making your cheat sheets, that helps you out. Okay. So we've done the magnetic field experiment with the slinky, right? And basically what we've shown is a changing magnetic field will give us current. Changing current will give us magnetic field, and we can do weird stuff. Okay? So what we're going to do is I've got a magnetic field. And I've got a current going through that magnetic field. Charge means I've got a charge that's moving at a velocity. We showed early on that my magnetic field, or my force to my magnetic field, was equal to this right here. We actually went back, and so I'm going to do this, and we're going to go back to that lovely charge density stuff just to get us to where we want to go, and that's why we do it, so you can actually see it. So if I take my length of wire, we have a potential for a number of free electrons, right? Because this is a conducting material. And if I look at that free electrons, I've got the area of my wire and its length is going to give me the volume. So I can get a number of charges per unit volume, okay? This gives me, and if I multiply that times 1.602 times 10 to the minus 19, this gives me the total charge. That's the total charge in that segment of wire. Okay? That's the total charge in that segment of wire. So now if I look at this force, I got my force is equal to my total charge in the segment of wire, velocity But this right here, if we go back to our charge density and go back to how we define current, that's just current. Okay? But that's not this length here. Okay, that's not this length. That length needs to come out. That's ALQ. That's current. And so I get LV cross B. And if I move the V over here, which I can do, that is something I can do, I end up with IL cross B. This right here, current is a scalar. And that right there looks familiar, sorta. Looks familiar, sorta. So let's look at this. So I end up, if I do an incremental force, and I have current, and this becomes an incremental piece of the wire, this becomes the total force. And if I go for the whole wire, we've got an R across there. So if we go back and look at torque, it's R cross F. We could rewrite our torque as I A cross B, and this A is the direction of the force. And we define this thing as mu, which is a dipole moment. So we're just going to go ahead and define that as a dipole moment. We get torque is going to be my dipole moment across from the magnetic field. So I think I drew this thing for you guys on Wednesday. We have a series of loops of wire. We have a conductor here with a potential across the bottom. And if I put a little magnet here, we end up with that torque part that's going to drive our little motor. And that gives us our little motor. And our dipole moment is going to be affected by the number of turns, the current in the wire, and the direction of our force. And that's the number of loops. And it turns out you could go ahead and you could play with potential energy associated with the magnetic field. Will give us our dipole moment dot product with our scalar. And then we can rewrite kinetic energy, which is 1/2 mv squared. But that v, when we showed it, we showed that cyclotron radius. That's mvqb. If I solve for v, I get v is equal to qbr divided by the mass. Plug that into there, and I get 1/2 mqbr m, all that squared. And then the kinetic energy in my magnetic field is going to be 1/2 Q squared B squared R squared divided by chem. So we can play with stuff. So we're going to take a proton traveling with a velocity of 2I minus 4J plus K meters per second. And it's going to enter a magnetic field of I plus 2J minus K, and that's in Tesla. We want to know the force on the proton. So force is going to equal the charge V cross B. So now I'm going to end up using my I, J, K, and we have to put the velocity first, so it's going to be 2 minus 4, 1. Magnetic field is 1, 2, minus 1. And we're going to get Q. And remember how to do these, right? Cover that up. So we're going to get, okay, I did it backward. Oh, okay, I'm going to get 4 times 1 minus 1, right? That's going to give me 4. Subtract off this part, minus 1. That's in the I direction. Remember, you get this weird negative thing that you have to do. And so I get negative 2 minus 1 in the J direction. And I do that part, and that's plus now. I get 4 minus a minus 4 in the K direction. So it's going to give me Q times 3I. It's minus 3 times minus is plus 3J. And that is plus 8K. If I wanted to calculate the magnitude of the force, that's going to be the charge times the square root of 3 squared plus 3 squared plus 8 squared. You guys let me get away with stuff. That's a 2. 4 minus 2, that's actually 2, and that's actually a 4. So this time I've got a circular loop. It's in a magnetic field. The magnetic field has a magnitude of 0.8 Tesla. Our loop has a radius of 2 meters. And there's a current of 17 milliamps. We want to calculate the magnetic moment. Mu is just going to be the current times the area, which means I'm going to take my 17 times 10 to the minus 3 amps. The area is, remember, area is pi r squared. That's 2. R squared is 4, so my area is 4 pi. So I'm going to put my 4 pi in there. That's going to give me 0.213, and the units are amps squared. We can now calculate the torque, which is going to be mu b. So it's going to be my 0.213 amp meter squared times my 0.8 Tesla, and that ends up giving me 0.171, and that works out actually to be Newton meters if you play with all the units to do the unit analysis. So you can get weird problems, and that's the trick on this one, is to figure out what the problem is actually telling you. So we're going to start out a problem that says, given a velocity is described by this. The electric field is going to be E in the K direction, and the magnetic field is V in the J direction. We want to figure out what the magnitude of the electric field is. But we're telling you that there's a 750 eV electron that is moving in the minus I direction undeflected. So this little electron has that much energy and it's moving undeflected. So we've got a lot of information here, but we don't necessarily know how to deal with it. Well, if it's moving undeflected, the force through the magnetic field and the force through the electric field have to be the same. So I can say, all right, my forces have to be the same. So my magnetic field is QVB, and my electric field is QE, so I can get rid of that part. Then I have to remember that this is an energy. And if it's moving, this is going to be kinetic energy. So that means 1/2 mv squared is going to equal my kinetic energy. And so I could solve for V. V is going to be 2 times the kinetic energy divided by the mass and the square root. So I can plug that back into there. So E is now going to equal 2 times the kinetic energy divided by the mass of my electron. Yeah. There we go. So my electric field looks like that. And so now E is going to be, my magnetic field was given as, oh, I didn't give you that. Oh, B actually was equal to 15 millitesla. So I get 0.015 Tesla. Square root of 2, 750 electron volts. But you have to convert electron volts to joules. That's 1.6 times 10 to the minus 19 joules per electron volt. Divided by the mass of my electron. And that ends up being 2.44 times 10 to the 5th volt meters. So the tricks to these is figuring out, this one literally is figuring out what forms of these equations to use, given the information that it gives me. So don't make it harder than it is when you guys are working the homework, but that really truly is the trick. And just so you have it, the solenoid equation, is L is going to end up being the number of turns times the flux divided by the current. And then you get the potential energy is going to equal 1/2 the number, the flux, times the current. And I think that's where I'm going to stop, because we're going to end up doing Faraday's law of induction and get Lenz's law, and then we're going to actually define this as inductance. And my inductor, okay, is going to be related, so this is that lovely little thing right here. When we see it in the circuit, and it's going to be in henries. And so our three devices that we end up with are our capacitors, our resistors, and our inductors. And the inductor is going to be an L, this is a C, and this is an R. And if this is instantaneous, one is going to lead and one is going to lag. And that's going to be important when we get to RC circuits. So I know I went through things a little fast. I would encourage you to look at the examples in the book, because that's really going to help you guys out big, big, big time. But we're just about there to our devices, and then we get to define Maxwell's equations, and then we get to go to electromagnetics. Yes! We'll talk about Poynting vectors. We'll have a history lesson soon. Well, we won't do it Monday, because we aren't having class on Monday. Having class on Wednesday. I will probably post a quiz on magnetism, because we got to get another quiz in there, and then we'll be good. Yeah? Hang on, I can't hear you very well. Okay, try it now.
Did you ever get my email?
I think I did. I think I saw it. I will holler at people on Monday if I didn't, because I'm going to try and get that stuff done Monday or Tuesday. FYI about Tuesday, I think I have to go to Woodward on Tuesday, so I may not be around during Tuesday day, but I may actually decide not to go because I've got too much on my plate. We'll just have to wait and see.